Hello friends. So in past few lectures you have learned the concepts behind the classifier, namely support vector machine, especially in case of hard margin classifier, soft margin classifier, and then what is kernel based support vector machine. So in this lecture we will learn the Python implementation of support vector machine, more specifically in terms of classification problem. So the agenda of this lecture is, as I told you, we will learn the implementation of hard margin and soft margin classifiers, SVM classifiers for a binary classification problem, and for implementation we will use scikit-learn utility of Python. We will demonstrate how we can apply support vector machine classifier for a synthetic data set having two features, so that we can have visualization also. We will also learn about the important hyperparameters in this implementation, means what are the important hyperparameters, those will change the hyperplane or those will influence the accuracy of SVM classifier. We will also learn about using inbuilt and user defined kernels, means how to implement a user defined kernels in case of nonlinear SVM. So, for this implementation again we will use Google Colab. So, let us come to our first implementation. So, in first cell of this particular notebook we are having we are importing the utilities. Like in first line you can notice we are importing numpy as np. In second line we are importing the plotting functionalities. Now when let me run it. Okay. Now let us discuss about second cell. So in this cell we are generating a synthetic binary classification data, and for this what we are doing, if you can notice in first line, from sklearn.dataset.sample generator we are importing make blobs. So what we are doing, in two dimensional plane we are generating some points, and how many points, that is given by number of samples, means we are generating 100 points, and those 100 points will be having two clusters, and the standard deviation of each cluster will be around 0.65, and for that what we are using, the functionality make underscore blobs. So what this particular command will give you, it will generate 100 two dimensional points, or in other way I can say 100 data points from having two features, one is x1 and x2, and from two classes, and class information or class label is given by y. So y equals to 0 and y equals to 1, and then after generating this synthetic data, what we are doing, we are plotting it. So for plotting you can recall my previous sessions, we are using plot.scatter, and from there we are here I am giving the first feature value of x, second feature value of input data x, and then color coding is given by the class information. So let me run it so that you can visualize the data. Okay. So here is the data set. So you can see it is a two dimensional data, horizontal feature and vertical feature, and data is divided into two classes, each one represented by different color. After that what we will do, we will first let us try to see some synthetic margin. So for that synthetic margin I am using some plotting functionality like np.linspace for generating my some xfit data, then again plt.scatter, and I am fitting some lines here. So if I run this plotting functionality, you can see the same data, but here I am having three different hyperplanes, and if you can see carefully, all these hyperplanes are more or less separating the data in a very fine way. However, which hyperplane my SVM will give you? So, the hyperplane which is having the more margin. So, if you see these 3 lines, the maximum margin is given by this center line. So, this is just a visualization of the concept of hard margin classifier or soft margin classifier. Now, let us try to import a support vector classifier. So, for that from sklearn.svm I am importing SVC. So, SVC stands for support vector classifier. So, whenever you have to apply support vector classification you have to do in Python, you have to write this command from sklearn.svm import SVC, and then you will create an instance of this SVC class. So, here I am doing it model equals to SVC, and then there are 2 important hyperparameters, one is kernel. So, I am going to discuss about these hyperparameters very soon. So, here I am taking a linear kernel, means I am using linear SVM, and then the value of capital C, that is your regularization parameter, and then I am having model dot fit x and y. Okay. So, once I run it, you can see here I am having now a support vector classifier with me, which has been trained on the given data, and you know it is a supervised classification tool. So, supervised classification algorithm. So, I am using class information also here, which is y. Okay. So, as I told you, there are some important hyperparameters. So, one is capital C, that is your regularization parameter, and it is basically responsible for the strength of regularization, and which is inversely proportional to C, must be strictly positive. If you take the very high value, we will going for the hard margin, but for a smaller value what we will going towards the soft margin, means we are allowing some of the misclassification, and I will show you that particular aspect also. Then we are having kernel. So, kernel, so by default this capital C will be having value 1. In kernel we are having different kernels like linear, polynomial, RBF, sigmoid and pre-computed. So, what you can do? You can define your own kernel also, we will take one example of that. By default we will be having RBF kernel, but as you can see here, I am taking this kernel equals to linear, since my data is linearly separable and I want to find out a hyperplane in 2 dimensional space, which is a line. In other words, I want to implement linear SVM, and then I am having this degree. So, this degree is nothing, if you are taking polynomial kernel, then the degree of the polynomial. In other case like linear or RBF, it will be ignored. Now, since I have fitted this, I have trained my SVM from the data. So, it means now I am having my hyperplane and supporting vectors. So, let me check that. So, for that again I am using this plotting utility, okay, by generating some linear spacing, some points x, small x and small y, and using the Ravel kind of thing by doing the reshaping. So, I am not going into detail of this plotting, but I am creating a functionality plot SVC decision function, and then I will use this plotting functionality to plot my hyperplane. Okay, so let me apply it. Okay, so here you can see. So, whatever you have seen, you have learned from Professor S.K. Gupta in the conceptual lecture in case of hard margin classifier, you can notice it here. we are having our separating hyperplane, and then we are having somewhere 3 supporting vectors, 2 from red class and 1 from yellow class. You can see these supporting vectors, what are the coordinates. For that you have to run model, which is my classifier which we have trained. It is an instance of SVC class, support vector classifier class, and dot support underscore vectors underscore. So, if I run it, you can see I got those 3 points, coordinates of those 3 points, or in other words the feature values of those 3 points. So, you can see how easy is this to apply SVM using scikit-learn in Python. Just like any other estimator, you have to basically pre-process your data and then just these 3 lines: import SVC, create an instance of SVC, define your kernel value of C, and then model dot fit capital X Y. If I take a very small value of this parameter, let us say C equals to 0.1. So, you can see now we are allowing misclassification. So, in that case it is going, although this data is linearly separable, it is going, this hard margin is going towards the soft margin classifier. Let us see some mixing of the data. So, from this from which I have generated the synthetic data, let me take here a bit more cluster, standard deviation of each cluster, and you can see, or let us take a bit more 0.95. Yeah. So, I am having some mixing. So, it is, the data is no more linearly separable, and certainly here we have to go for soft margin classifier. So, in Python implementation only this capital C will change. So, earlier I was taking a large value, now take a very small value like 0.1, and let us see what kind of classification I will get. Let me plot the classification boundary, and you can see here. Okay. So, here it is allowing some misclassification. So, this is the implementation of linear SVM. Now, let us move to kernel SVM or nonlinear SVM. So, you can see the data now, data is no more linearly separable. I need some sort of circular or elliptic kind of boundary, and when I apply the linear SVM, you can see what kind of classification I am getting. Since so it is totally wrong classification, wrong hyperplane, because we have chosen a wrong model. So, what we need to do? We have to go for kernel SVM. So, what I will do? This is a 2-dimensional data. First, I will project it to 3-dimensional, and for the one is your, let us say the horizontal axis is x, vertical is y. So, the third direction will be e raised to power minus x square plus y square. So, RBF sort of function. So, like you can see, for that I can do np dot exponential minus x square dot sum 1. So, it is nothing, just if first feature is x, second feature is y of these data points. So, it is e raised to power minus x square plus y square. So, let me run it, and now I will apply my RBF kernel to this non-linearly separable data. So, just you can see I am not doing anything, I am just changing my kernel, nothing else. Earlier I was taking the linear kernel, now my kernel is radial basis function, and then CLF dot fit, because CLF my model, classification model, and I am using dot fit functionality on it. Okay. So, I am having now my nonlinear SVM, which is trained on this non-linearly separable data. Now, let us try to plot it. Yeah. So, the same functionality, and now you can see how good boundary we are getting. So, now my this is the separating hyperplane. which is a sort of nonlinear, or I will say the ellipse kind of thing, and these are then supporting vectors. So, we are having quite large number of supporting vector in this case. We can see how many using the CLF, that is the model name dot support underscore vectors underscore, using this command, and if I run it, you can see all these are my supporting vectors. So, this is very first implementation which I am doing, and this is just for the training. Now, whenever we do go for a classification problem, what we do, we split our data into training and testing, and then from the training data we train our classifier, from the testing data we evaluate the performance. So, that we will do very soon. Okay. So, using this particular notebook, the first exercise, using this piece of code, you just see the implementation of all the concepts which you have learned theoretically. Now, I am coming to the second implementation. So, in this particular notebook, just I will show you the different kind of kernels. So, I am in the first cell of this notebook, I am importing utilities like numpy, matplotlib.pyplot and sklearn. Import SVM, that is all. So, these I am importing. Then what I am doing? I am having some data set and their target. So, this is I am denoting by x is the 2-dimensional data, and then y is target value sum. So, some synthetic data I am generating, not even yeah, I am defining some data, 2-dimensional data. Now, I am having kernels. So, here I am using for loop, and my kernel will go run over this list of the kernels, which is linear, then poly, and then RBF. And then you can see now my CLF is nothing just svm.svc. So, if you are a bit so here I have from sklearn import SVM. So, let us go like the earlier case only. So, sklearn.svm import SVC. Okay. And now, when you are creating an instance of it, so you can write SVC. So, like the earlier one. So, now I am having 3 kernels on the same data, linear, polynomial and RBF. Here you can see one more hyperparameter gamma, and that is the width of RBF kernel. So, let me run it. So, you can see this is the linear kernel, this is your polynomial kernel, polynomial kernel, and finally RBF kernel, and these are the classification. So, in that way you can use the kernel. However, sometimes we need to implement our own kernel. So, how to define our own kernel? For that I am giving you a very small implementation. So, here again how to define custom kernel. So, what I am doing now, I am taking a benchmark data set, and that benchmark data set is Irish data set. You are well aware of this particular data set. So, in first cell of this third notebook, I am importing utilities numpy, matplotlib.pyplot, and then from sklearn I am importing SVM as well as data sets. From data sets I am loading the Irish data. In capital X I am saving the input feature, and here I am taking only first 2 features because I want to plot this data. Originally this Irish data is having 4 features, if you can recall from one of the previous session, that is petal length, petal width, and then sepal length and sepal width. So, it is a 4-dimensional data, but I am taking only first 2 dimensions, and in Y I am having Irish target, which will be like Virginica, means which is because these Irish flower are coming from 3 different classes. So, let me load it. Okay. Now, this is the important one where I am defining the custom kernel. So, define my kernel which is a function running on 2 vectors x and y, and now you can see I am having this 2 dimensional array numpy array which is having the first row entry as 2 1 and second row entry is 1 3. So, in that way what I will be having? I will be having now kernel as x transpose A into y. And why I am taking this 2 by 2 matrix? Because my data is having 2 features. If my data is having k number of features, I need to take this as k by k matrix. It will be a quadratic form, and then you can see it will be something x transpose into this matrix M into y, where x transpose is a 1 by 2 vector, M is 2 by 2, and then finally y is 2 by 1. So, ultimately you will get a single value. Okay. So, in that way you can define your own kernel. So, I am having this kind of kernel here, let us say 2 and 1. So, let me run it. Now, here I will use my kernel. So, now you can see the kernel equals to my underscore kernel. So, I will be having at this moment this kernel, and this kernel is 2 x square plus y square. If I am taking 1 here, it will become x square plus y square. If I am taking minus 1 here, it will become minus x square plus y square. So, let us take 2 x square plus y square. Okay. So, now my SVM object is there with the name of CLF, which is already trained on the given data, and now let us see the plotting and the decision boundaries on this iris data, and you can see. Okay. So, in that way I can have different kind of kernels, means custom kernel which you want to implement, and that you can implement using this quadratic form of the matrix. Okay. So, this is my third implementation of this particular session. So, what we have learned? We have learned how to apply SVM, how to create SVM instance, then how to use fit function, how to plot decision boundaries, what are the importance of different kernels, what is the importance of capital C regularization parameter, and what is gamma, that is your width of the RBF kernel. So, basically I can say in this lecture we have just visualized the concepts. In the next lecture we will apply this SVM classifier to real benchmark data sets. Thank you very much.